what is fine-tuning? Now let's delve into why fine-tuning is considered expensive compared to retrieval-augmented generation, also known as RAGs. Fine-tuning is a machine learning technique used to adapt a pre-trained model to a specific task or domain by further training it on task-specific data. This process involves updating the parameters of the pre-trained model using task-specific labeled data, allowing the model to learn task-specific patterns and improve its performance on the target task. How fine-tuning works. First, start with a pre-trained model that has been trained on a large and diverse dataset, typically using unsupervised learning objectives such as language modeling or image classification. Next, collect or create a labeled dataset specific to the target task or domain. This dataset contains examples relevant to the task you want the model to perform. The fine-tuning process involves initializing the pre-trained model with its learned parameters. Then, train the model on the task-specific dataset, adjusting its parameters or weights to minimize the loss function specific to the task. Iterate through multiple epochs, adjusting the parameters to improve performance on the task. The resulting model is fine-tuned for the target task and can be used to make predictions or perform other task-specific operations. Use case sentiment analysis for customer reviews. Imagine a company wanting to build a sentiment analysis system to analyze customer reviews and determine whether they are positive, negative, or neutral. The fine-tuning process would start with selecting a pre-trained language model such as BERT or GPT, which has been pre-trained on a large corpus of text data. Next, task-specific data collection involves collecting a dataset of customer reviews labeled with their corresponding sentiments: positive, negative, or neutral. Fine-tuning the model involves initializing the pre-trained language model with its learned parameters, then fine-tuning the model on the customer review dataset, adjusting its parameters to minimize the loss function for sentiment classification. Train the model over multiple epochs, refining its ability to classify sentiment accurately. Finally, evaluate and deploy the fine-tuned model on a separate validation dataset to assess its performance. Once satisfied with its performance, deploy the model to analyze new customer reviews and extract sentiment. Use case resume screening for job applicants. Consider a human resources department that needs to automate the process of screening job applicants' resumes to identify qualified candidates for a specific job opening. The fine-tuning process begins with selecting a pre-trained language model such as BERT or a domain-specific model like BioBERT, if the job opening is in a specialized field like biotechnology. Task-specific data collection involves gathering a dataset of resumes labeled with their suitability for the job opening, such as qualified or not qualified. This dataset may also include additional information such as job descriptions and applicant profiles. Fine-tuning the model involves initializing the pre-trained language model with its learned parameters. Then, fine-tuning the model on the resume dataset, adjusting its parameters to minimize the loss function for resume classification. Train the model over multiple epochs, refining its ability to classify resumes accurately. Evaluate and deploy the fine-tuned model on a separate validation dataset to assess its performance. Once satisfied with its performance, deploy the model to screen new resumes automatically. Let's walk through an example workflow for using AI in hiring. First, we start with a pre-trained language model like BERT. Next, we gather a dataset of resumes labeled with their suitability for the job opening. We then fine-tune the pre-trained model on this resume dataset, adjusting its parameters to classify resumes accurately. After fine-tuning, we evaluate the model on a validation dataset to measure its performance metrics such as accuracy, precision, recall, and F1 score. Finally, we deploy the fine-tuned model to automatically screen new resumes as they are submitted for the job opening. Now, let's explore the benefits of fine-tuning in HR. Firstly, efficiency. Automating the resume screening process saves time and resources for HR personnel, allowing them to focus on more strategic tasks. Secondly, consistency. The fine-tuned model provides consistent and unbiased evaluations of resumes, reducing the risk of human error or bias in the screening process. Thirdly, scalability. The automated screening system can handle a large volume of resumes quickly and efficiently, scaling to meet the organization's hiring needs. Lastly, improved candidate experience. Candidates receive prompt feedback on their applications, enhancing their overall experience with the hiring process. Overall, fine-tuning a pre-trained language model for resume screening in HR improves efficiency, consistency, and scalability, leading to more effective and streamlined hiring processes. Why is fine-tuning expensive compared to RAGs? Well, fine-tuning typically requires a large amount of labeled data for the target task. Collecting and annotating this data can be time-consuming and expensive, especially for complex tasks or specialized domains. Additionally, training a pre-trained model on a task-specific dataset requires significant computational resources, including powerful GPUs or TPUs and high-performance computing infrastructure. The training time for fine-tuning a model can take a considerable amount of time, especially for large-scale models and datasets. Training may need to be repeated multiple times with different hyperparameters to achieve optimal performance. Moreover, fine-tuning often requires expertise in machine learning, data preprocessing, model selection, and hyperparameter tuning. Hiring or consulting domain experts can add to the overall cost. In contrast, while retrieval-augmented generation, RAG, also requires computational resources for training and inference, it may not require as much labeled data or fine-tuning effort. RAG systems leverage pre-trained models and retrieve relevant information dynamically, reducing the need for extensive fine-tuning on task-specific datasets. Additionally, RAG systems benefit from the pre-existing knowledge stored in large-scale language models, further mitigating the need for extensive fine-tuning. Overall, the resource requirements and costs associated with fine-tuning can make it more expensive compared to RAGs, especially for certain applications and domains. Let's compare fine-tuning and retrieval-augmented generation, RAG, in the context of personalized product recommendations in e-commerce. Fine-tuning involves training a pre-trained language model, like BERT or GPT, on task-specific data, such as user behavior data and product attributes, to improve its performance on a specific task, such as personalized product recommendations. During fine-tuning, the parameters of the pre-trained model are adjusted to minimize the loss function specific to the recommendation task, optimizing the model's ability to predict personalized recommendations. For example, in e-commerce, fine-tuning requires a labeled dataset of user interactions and product attributes. The model's parameters are adjusted based on user feedback and product features to minimize the loss function, improving the relevance and accuracy of personalized recommendations. On the other hand, RAG systems integrate retrieval-based methods with generative models to provide more accurate and contextually relevant responses. Instead of fine-tuning a single model, RAG systems dynamically retrieve relevant information from a knowledge base and generate responses based on the retrieved information. For example, in e-commerce, the system retrieves relevant product information from a database based on user queries and preferences. Using the retrieved product information, the system generates personalized product recommendations tailored to the user's needs and preferences. Key differences include training data. Fine-tuning requires labeled data specific to the recommendation task, while RAG relies on a knowledge base or dataset containing information relevant to the task, but does not require labeled data for training. Model optimization. Fine-tuning adjusts the parameters of a pre-trained model to optimize its performance on the recommendation task, while RAG dynamically retrieves and generates responses based on the information available in the knowledge base, without directly adjusting model parameters for the task. Flexibility. Fine-tuning tailors the model specifically to the recommendation task, but may require retraining for different tasks or domains, while RAG can be more flexible and adaptable across different tasks, as it leverages retrieval for context and generation for response synthesis. Resource requirements. Fine-tuning can be resource-intensive, requiring labeled data, computational resources, and expertise for training and optimization, while RAG may require less training data and computational resources, as it combines pre-existing knowledge with dynamic retrieval and generation. In summary, fine-tuning involves training a pre-trained model on task-specific data to optimize its performance, while RAG integrates retrieval and generation to provide contextually relevant responses without directly adjusting model parameters for the task. Fine-tuning is more tailored to a specific task, but can be resource-intensive, while RAG offers flexibility and efficiency through dynamic retrieval and generation. Subscribe to our channel, and don't forget to hit the like button if you enjoyed this video. Also, please comment if you have any interesting topic on AI.